Hey guys, welcome to the show today. We're with Dr. Blitz today, and he's going to talk to us about some Big Bang facts, something about physics, all about his credentials, things like that. We're going to go and ask him some questions about space, time, and all kinds of stuff that you guys want to know about. So welcome on, Dr. Blitz. How are you?
Thanks for having me. I'm doing all right.
Great, great. Yeah. So just I want to know more about you, a little more, for the audience as well. Like, what are your credentials, and what is your actual position?
Yeah, so despite the appearances to the contrary, I'm not actually in space. I'm a postdoctoral fellow or a postdoctoral researcher, whatever you want to call it, at a university somewhere in the heartland of Europe. I'm not going to give away too many details because I try to keep some anonymity here. But I work in a math department. I have a PhD in physics that I got from a university in the United States, focusing in mathematical physics, if you will.
Hmm.
I do. I've published quite a few times for my age, anyway, in mathematics journals. I recently got a paper published in a physics journal, so I'm kind of all over the place, but it all ties together at the end of the day.
Cool. How old are you, by the way, if you mind me
30.
asking? 30. Okay. Cool. And now I know we know you from TikTok and everything, and you probably know me from TikTok. I'm always debating and stuff. Um, so what is your position on that? Like, in atheism, are you agnostic, atheist?
I mean, I. I mean, I am an atheist. If you want to call me an agnostic atheist, that's fine. People will ask me, "How sure are you?" And I say 98% or 99%, something like that.
Okay. All right, great. So yeah, let's get into the science here. Um, a lot of people when we discuss about the origins of everything, we talk about the Big Bang, right? The number one thing they say is the Big Bang. Do you believe in the Big Bang? And what I want to do is pretty much like clear things up for them. So just kind of like summarize the Big Bang, and because a lot of people say, well, it's just a theory, but just
Yeah.
find out what theory means in science and why it's different than the typical colloquial use of it.
So it's hard. It's not hard to say. We just have to be really specific. I mean, people
Mm,
get mad at me in TikTok debates because I really I play semantic games, if you will. But that's because precision matters when we're trying to communicate big ideas, right? So when we talk about the Big Bang, if you ask a cosmologist, what I'm not one, by the way, but if you ask a cosmologist what they're thinking of when they hear Big Bang, they're thinking of something called the concordance model, typically, also known as lambda CDM. Now,
mm,
the concordance model, or lambda CDM, is it's a model that uses general relativity. The lambda is the cosmological constant in general relativity, and CDM stands for cold dark matter. So putting general relativity, the cosmological constant, this is dark energy, and cold dark matter together, and you get basically the evolution of our universe from 13.8 billion years ago until today. So when we're talking about the Big Bang, we're talking about the universe being in some state 13.8 billion years ago, the observable universe perhaps being the size of a basketball, and then evolving for the last 13.8 billion years until now. Now, importantly, it is the consensus amongst most cosmologists, most physicists, I would even say, that the Big Bang does not stipulate that the universe began with a singularity. Rather, the Big Bang, if we take the concordance model and we drive it all the way back to t equals 0, we understand that the universe that's predicted, or rather, we understand that the what the mathematics predicts cannot possibly line up with reality because we don't have an understanding of physics that could have taken place before a certain amount of time, before the universe was about the size of a basketball, the observable universe. And the reason we say that is because the universe was very, very hot. Gravity was very, very strong. You have quantum mechanical effects, gravitational effects, all of these things playing together that we just don't understand. So we say the Big Bang stops when the universe is, the size of a basketball or whatever. Well, then you can ask what happened before that. Well, the current best model is something called inflation. I have a video on that, not to show for myself.
mm.
Um, but inflation just explains why our universe took on the behavior that it did. But then you could ask what happened before inflation, and who knows? But probably not a singularity.
Right. Okay. Great. So, um, now at the earliest part of the universe, what we see is like basically like this quark gluon plasma, right? Where it's like this high energy density particles that exist. That's pretty much what we know, pretty much. Is that correct?
Yeah, that's where the standard model of particle physics basically stops. It's right about there.
Right. And then when it comes to inflationary cosmology, we have, I think, people like what's his name, Guth, talking
Yep.
about inflation, where you have like an inflaton and then it inflates and expands into space and time, or just that particle or that field that inflates itself and
Yeah, yeah,
becomes.
yeah. So the idea is that during inflation, space and time existed. It's just
Mm,
rather than having a whole bunch of stuff, you have a single thing, or perhaps multiple things. One of which is called the inflaton. The inflaton being in a very high energy state, and as a result of this very high energy state, it kind of forces the universe to expand in the same way that dark energy does today. And then
mm,
over time, it kind of rolls down this hill. It's called slow roll inflation. That's the currently most agreed upon model, although it's still a hypothesis. Um, Eventually, it rolls down the hill all the way, and then it decays into all of the particles that we know today, or rather, the quark gluon plasma that you were describing.
right. Um, so the point is like when we say beginning, right? A lot of people want to know where the beginning of everything is, but they have to realize that beginnings are very arbitrary in physics. Would you say so?
Um, I would just say that it'd be great to have data about the beginning, but as far as data goes, we go back to, like you said, the quark gluon plasma. Anything before that is model building and testing the limits of our knowledge. We just don't have knowledge that there even was a beginning.
Right, right. And there's different types of beginnings, like an absolute beginning. Then you have like, would you agree that there's different types of
Oh
where you
yeah, sure. So people might say that like the Big Bang, the Big Bang was the beginning of time, whatever. I would think that more accurately we should probably call it a phase change.
right,
The t equals zero of the Big Bang might be better described as a phase change of our universe. It started to behave in a completely new way.
exactly. Yeah. So for everybody watching, just that the Big Bang, just think of it as a phase change where you have high energy state becoming this state we know of today as the universe. Um, Now, in terms of causation, a lot of people want to say what caused the Big Bang, right? The same thing applies, right? Would you say that you can have a fundamental space-time that precedes everything else? It's just eternally there, and from that space-time, or we call inflate or scalar field, right? It
Yeah,
was
yeah.
it was always there, and then inflated. Parts of it inflate into the universe we know today.
Maybe. So, a month and a half ago, I would have gone onto a big diatribe about, we don't know what caused it. Maybe there's infinite causation. But I've been reading, and not to shill for him, I've been reading Sean Carroll's book, Something Deeply Hidden, or rather, I've been listening
Mm,
to it on audiobook. Quite good. I'm only halfway through. But he brings up this question. Maybe it was in one of his podcasts. Anyway, he brings up this question of why do people care or ask about causation? Like
mm,
the idea of causation of every effect has a cause, that kind of thing. That goes back to Aristotle, but that's not how we think about physics anymore. We don't think about
mm,
physics or the nature of reality as in terms of causation. We think of in terms of dynamics, and we think in terms of interactions. So we say
mm.
that you have some state, and that state has dynamics, and it evolves in a particular way as a result of those dynamics. And maybe there's self interactions that lead to complicated dynamics, but none of that says that there's a cause for it. It just is a way.
Right, exactly. And I mean, Sean Curl, he agrees to he holds to the many worlds interpretation, where the universe is just this one big quantum state that is eternally existing. That's what he doesn't. Is that what he holds to?
I don't. So I suspect probably. He's definitely a serious proponent of the many worlds interpretation.
Yeah, yeah,
I mean, I can blame him for basically all of my philosophical views. I am too. I've been follow. He's a bright guy. He's an excellent physicist and an excellent philosopher.
right. Yeah. So now, when it comes to the block universe, I watched one of your videos on the block universe. I've made a video on it as well. It really intrigues me how the idea of time itself is something that really is it's a real thing, but the passage of time is really could be an illusion to us. Um, so I just want to just get your opinion on the block universe and what that means. Because a lot of theists will use the argument, well, the universe changes, subject to change, therefore it can't be necessary. But when it comes to the block model, we know that the universe itself as a whole could be just this one static chunk that exists
Yeah,
without any change inside of it.
we have to be really, really careful when we talk about static, when we're talking about time itself being static, right? Because static is a word used to describe things that don't change in time versus things that do change in time. So unless
Right.
there's some sort of meta time in which the block universe is sitting, it doesn't really make sense to talk about static or
Right.
not. But the
Right.
idea of the block universe is basically one of determinism or not. If the universe is deterministic, then there's no difference between, say, the past and the future. The one must precede the other must postcede the first, right?
Mm.
They're all there is no preferred moment, if you will, even though we may experience it that way. The whole notion of necessity versus non-necessity, contingency, I guess is the word. I don't know. I always think those arguments are kind of silly.
Yeah, I mean, I don't see anything stopping the universe itself from being a necessary state. I don't know why theists have to add God. Um,
Well, but that's not even the language that we talk about when we talk about science. We don't talk about necessary versus contingent. We just talk
yeah,
about, look, is there a model that describes reality that's self-contained? If so, then it's a perfectly good model of reality. If it's not self-contained, well, then you need something else that contains it. That's all.
exactly. Yeah. Um, and now in terms of in block universe, I mean, um, like you said, like we can slice time into chunks. We can slice into slices. And then, I mean, in terms of our existence here within the block model, would that be like just a series of events that go on forever, like this elongated structures?
Well, I don't know about you, but I'm probably not living forever. Um, yeah, I mean, yeah. So you can think of the language to use is a world line. A world line of a given
Mm,
atom is basically the path that that atom tracks out through the universe over time. And so
right, right.
instead of thinking of an atom as a like a point or like a small thing, you think of it as like a line in space time.
Right. Yeah, it's really mind-boggling stuff to actually think about it, to grasp your head around it. Um,
Just don't think about it too much.
yeah, yeah. This is why it's hard because people just can't grasp like well, nobody can grasp four dimensions.
Yeah.
But how would then how would this fit in like the expanding? Like, does this contradict like quantum mechanics? Like, how would this fit in an expanding universe?
Um. So so an expanding universe just suggests that the block is growing, right?
Mm,
Or that the block is wider on one end than it is on the other end,
mm.
if you will.
Yeah, yeah.
Um, Alternatively, the universe might just be infinite in size, in which case it's the same size everywhere. It's just more infinite on one side than on the other. People are going to get mad about that, but what can you do? As far as quantum mechanics goes, the block universe is almost like a classical description of the universe we live in. It arises from general relativity, where we think of three dimensions of space and one dimension of time as being kind of all the same thing, and we treat three dimensions of space as just existing, so why not time? However, there arises a problem when we start to try to think about what our universe looks like fundamentally on a quantum scale. And if you take the many worlds interpretation seriously, like the universe, like the space time itself, is an emergent phenomenon. It's just a thing that happens to look like it exists when you zoom out far enough. But on a small enough scale, space and time cease to have meaning. At least that's in one possible understanding of what our universe looks like at the most fundamental reality.
Okay.
So, block universe may go the way of the dodo, if you will, once we have quantum gravity, but who knows?
Right. Um, Now, well, is there consensus among scientists about like presentism versus eternalism? Is there consensus, or is it
No,
just
that's for
everybody's?
philosophers. That's for
Yeah, yeah.
philosophers. I
Or
mean,
in terms
if
of the universe being infinite, or
oh, I would. So okay, I'm probably if you is this on YouTube? Can I say things that would get me banned on TikTok?
no, it's fine. I don't
Okay,
care.
so if you put a gun to a physicist's head, at least a cosmologist or an astrophysicist or whatever, if you put a gun to their head and said, "Is the universe finite or infinite?" My guess is they'd say infinite, if only because that is kind of like the most parsimonious, the most simple option that we have right now that's consistent with the data. It is kind of disturbing almost to think that there isn't an end, but I mean, in my view, it's very disturbing to think that there is an end. That seems very wrong. So but there isn't consensus in the sense that we have scientific, rigorous empirical data. We have data that is consistent with it, but we can't see the entire universe. The universe um, could be like, like the surface of the Earth, and that it's like a ball, but 3-dimensional instead of 2, but just huge. In the same way that if you look outside, it looks flat, but the Earth is just big.
Right. Right.
It could be that a universe looks flat, but the universe is just really big.
Right. Exactly. You can barely measure the curvature. Well, we don't have the technology
Yeah.
to do that yet.
Well, we can measure the curvature, but it's consistent with 0 within our measurement error. So that's the problem.
Yeah.
If we get better measurements and we get, and we find out that it's actually positive or it's actually negative, we talk about positive or negative curvature or 0, then we'd have an answer. It wouldn't, if it's negative, then it's almost certainly infinite. If it's positive, then it has to be finite.
Right. And then if we contract the universe back to, the Big Bang itself, you go further back, like there could be a multiverse, correct? There could be many
There
different
could
types of
be. I don't
universes.
subscribe to it, but there could be.
Yeah. Well, is it because you just don't, is it because mathematically it doesn't work, or is it because you just don't have enough evidence for it?
It seems like it's basically the latter. I mean, we don't need it to explain anything, it seems.
Mm.
And it seems like if you take it seriously in order to explain something, it feels like a crutch.
Okay.
Now, by the way, I should specify that that doesn't mean that there aren't different regions of the entire universe that might have different laws of physics. That very well may be the case. Maybe the constants are slightly different in different parts of the universe that are very, very distant. What I'm talking about is like actually universes that are separate from ours, that are like unreachable, even in principle, kind of thing.
Gotcha. Yeah, because I mean, if our plane is infinite, then you can have other regions where there's different stuff,
Yeah.
different universes, like entirely. Okay, cool. And then now a lot of theists will talk about like outside of space and time, but to me it seems like every time we imagine something, we're imagining it within space and time. Like it's just the way our brains see
Mhm.
things. It's just how our brains can operate. Well, perceive things. So is there any coherency behind the notions of like being outside of space and time
I mean,
in
if you ask
physics?
me, the answer is no. And in fact, that's the argument I bring up most to theists who are very vague about what they mean when they talk about theism. Like if they're just talking about like some sort of deistic thing, the line of argument I run down is does your deity have a mind? Is your deity capable of thought? Is thought the change of mental state? Are they outside of time? And now you have a contradiction because in any reasonable sense of the word time, time just describes the ability, or time just describes the thing through which change is possible. And so if you have change, at least in my view, and I'm sure philosophers have thought about this before, but at least in my view, if you have change, you necessarily have time. And so it seems impossible to have any sort of decision making or thinking if you exist outside of time.
Right. So I guess time would just be the way we perceive change, and then time itself to us would be an illusion. Really, I mean, the passage of it would be an illusion, like the idea that it's moving.
I mean, sure. Yeah, if you take the block universe seriously, sure.
Mm.
If you don't, well, then time can be perfectly coherent. But importantly, there is a distinction to be made when we talk about time. So when we talk about physics, like time in a physics sense, we're talking about something called metric time usually. And I think Danny's brought this up before. For those of you who don't know Danny, well, too bad. But there's this thing called metric time, which is basically time that we can demarcate in duration: 1 second, 2 second, 3 second.
Mm.
There's a certain amount of time between events. But then there's a different type of time, metaphysical time maybe, which is just a chain of causation with no measurable, not with no measurable duration,
Unit.
but rather there is no way in which you could measure it. It's just this thing happens before that time, and that is a valid notion of time. You can 100% consider that. You might call it like projective time or something like that. But the argument is that if you want to have some sort of deity, some sort of like deistic deity or whatever, then it must exist at least in some sort of metaphysical time, if not metric time, because it must be able to undergo some sort of change.
Right. Okay. And then now when it comes to quantum field theory, I love this idea that there's a more fundamental feature of reality where, things can emerge from. Now, would it be true to say that quantum fields would be the most fundamental, like, constituents of reality, or, would that be a proper way of describing quantum field theory?
If you ask a phenomenologist or a experimentalist, they'd probably say yes, and they're wrong. Um, no, that's too mean. So as far as we can tell, quantum fields are not made up of smaller things, whatever that might mean. But again, when we do science, when we do physics especially, we're talking about models that describe the universe. So often people will be like, well, what is an electron? And I'll be like, well, it's an excitation in a quantum field. And they'll be like, well, what's a quantum field? And I'm like, look, it's just a way that we describe this thing that we live in. I don't know if quantum fields exist. I mean, in some sense, of course they don't. They're mathematical objects. They're not like physical things, but they're at least the most fundamental thing that we've been able. They are the most fundamental thing that we have come up with that can describe the universe. Now, I'm under no illusions that we will come up with nothing better, nothing deeper. Maybe
Mm,
it's string theory. Maybe it's something that nobody's come up with yet. Maybe there's some sort of like gravito. I don't know. Something to do with gravity. I don't know. This is all to say, quantum fields are certainly a very convenient calculating tool, and it's useful to talk about them as if they're like ontologically real. But in physics, we don't talk about like ontological reality. We just talk about
right.
models.
Right. Now these quantum fields, I mean, is this how, like, when it comes to particles, we know that they can also be waves, correct? So would this tie in with quantum field theory in some way, or?
So so again, I'm a proponent because of Sean Carroll. That man's brilliant. I'm a proponent of the many worlds interpretation, and in the many worlds interpretation, there are no particles. They're just
Mhm.
waves that
Yeah.
sometimes behave like particles, or in that they have particle-like characteristics. They're localized, but they're still just waves. They have wavelengths. They have frequencies. They're not points in any sense of the word. Um, Now, it turns out that it's a good approximation to treat things like particles in some cases. Like when we're talking about colliding protons, you might
Mhm.
talk about them as like actually being particles colliding at a certain moment in time, right? But it's all just an approximation. Really, it seems like fundamentally, again, talking in terms of models here, that waves are the most accurate description of the world around us.
Okay, interesting. So I'm guessing you would, and then, so particles would be like a property of waves, or would
Particles would
particles
be
emerge from?
they would be a good approximation of wave. They would be a useful and good way to approximately describe a complicated state in some situations.
Gotcha. Okay. Um, and I don't know if you know much about many worlds, but is it imply like we're entangled with the world around us, and then and then when something happens, when some kind of quantum event happens, we disassociate with that environment again, and then another world splits from that, branches out. Is that generally what it means?
Sort of. Unfortunately, people take the worlds too literally in many worlds.
Hmm.
The idea is as follows: you have so you'll have to bear with me, audience. For those of you who don't know about quantum superposition, you're welcome to the ride, right? So imagine that you have an electron, right? An electron can be in a superposition of let's say spin up or let's not even say spin. Let's say it's to my left. This is my left. It's a superposition of to my left and to my right. It's just its position. It is in a combination of left and right of me. Now, before I measure it, it's kind of just there doing its own thing, being in a superposition, happily being in both states. The idea behind many worlds is that when I go to measure where the electron is, I become entangled with that electron. And as a result of me being quite large and macroscopic, um, the rest of the world basically instantly interacts with me and therefore becomes entangled with the electrons. But the important piece is that when I become entangled with the electron, that means that there will be one piece of the superposition of me that's entangled with the left piece of the electron, one piece of the superposition of me that's entangled with the right piece of the electron. So now there's effectively I am now in a superposition. One is me and the electron is left, and the other is me and the electron is right. And then almost instantly, the universe will do the rest of the universe will do, well, propagating outwards at light speed anyway, will do the same thing to me, because now I'm in superposition and the universe is interacting with me. And so what you end up with is very, very rapidly, you end up with two copies of me, but they're not in separate universes. They're just two different pieces of the same wave function that can no longer interact with each other because they have decohered, if you will. But they're not like it's not like something splits. It's not like energy is divided in half. It's still the same amount of matter. It's just the quantum state has changed, and it's changed in a way that it's changed in an irreversible kind of way. In the same way that you can't uncrack an egg, you can't unsplit a wave function, but it's still one wave function. There's not like separate universes. We're not talking Marvel here.
Right. So in that case, we would all exist in superposition always.
Yeah, but the important point is that you're not all of them. You are one of them. Think of it this way: whenever a measurement happens, some sort of quantum interaction, the you that did the measurement gives birth to multiple of you, and then you all go your separate ways.
Right.
Yeah.
So there really could be multiple me's out there. Well, where we can't talk to.
There are, and they're in. I mean, at least the recent. Well, I mean, if you take the many worlds interpretation seriously, which I do, there are, and the recent ones are literally right on top of you. But it's like a ghost, right? There's a ghost you that's interacting with the ghost microphone and using the ghost computer, and you can't interact with the ghost world, and the ghost world can't interact with you, but you're all in the same place.
Yeah, that's profound. That's crazy to think about.
It's almost the interesting thing about the many worlds interpretation is that it's almost, in some sense, it should really be the default position.
It should be. It
should be, because all you're doing is you're just taking. So we know electrons can be in superpositions. This is well known. And we're made of electrons and protons and neutrons. All of those things can be in superposition. We know that systems can be in superpositions if they're composed of systems that can be in superpositions. So there's no reason to think that we can't be in superpositions. What the Copenhagen interpretation does, what all these other interpretations do, is they come up with a clever way of throwing away everything but one piece of that superposition. So they're just adding more assumptions to make it, more closely line up with our intuition.
Right. And then, yeah, it'd be more like Occam's razor, just be more simpler way of explaining reality. Instead of having the wave function collapse, it just does, and it just never does.
Yeah, right? It's just a wave function doing wave functiony things.
Wow, that's crazy. Okay, and then now when it comes to string theory, do you know much about string theory, or is that
a year of it? Yeah,
a year of it.
Yeah, okay. It's required.
Cool. How do you feel about that? I mean,
it's really complicated.
It's complicated.
Yeah, string theory is hard, man.
It is.
I mean, look, string theory is really cool, and like, there's a lot of really. Here's something to comment on that people will care about. String theory is not dead. It's not like being disowned by academia. Like, there's like kind of these stories going around that like, oh, everybody's like disowning string. No, they're not. If you go to any like a physics department in the world that has a theoretical physics division, there are going to be string theorists there. Like, there will be way more string. Just the odds of finding one person doing any other type of quantum gravity or theory of everything. The odds of finding one person doing something else besides string theory that's doing some sort of like fundamental physics stuff is like zero. The university that I did my PhD at, there was one guy who did quantum gravity that wasn't stringy, and 6 or 7 people who were doing string theory. So it's just not dead. Now, that is to say, it's not the same thing that people thought it was going to be 20 years ago or 25 years ago.
Yeah.
The hope of, maybe I should say 30 years ago, the hope that string theory would just quickly and easily lead us to a theory of everything, it's not dead. Well, actually, it is dead in that it's not going to be quick. We now know that string theory is a lot more complicated than we thought it was. And it will require there's not just one string theory. That you may have heard that there's somewhere between 10 to the 500th string theories and an infinite number of string theories, depending on who you ask. And finding out which one of those represents our universe, if any of them do, is a very hard question. But string theory as a framework is fascinating and has led to a lot of actual real physics. Notably, in 97, 98, 95, something like that, there was a fellow named Juan Maldacena came up with a paper about the holographic principle, namely the
Mm.
ADS-CFT correspondence, really, really famous. I think it has like 10,000 citations, which is huge. And this is a stringy paper. It relates n equals 4 super Yang-Mills width to ADS5 cross S5 string theory and a super gravity limit. There's a whole bunch of jargon words. It doesn't matter. Point is it's a string theory thing. And it kind of revitalized this notion, or almost even invented it. Didn't quite invent it, but almost did. This notion of holography, which is now a huge deal. And it has tons of applications and tons of very interesting consequences, even outside of stringy physics. In fact, I remember when I was preparing for my oral exam, I allegedly I was doing like holography things. One of the things that I mentioned is that, look, even if you don't like string theory, this holography actually has made actual predictions and helped us understand actual physical systems in condensed matter, which is like it's the physics of like, atoms and like nano structures and, spin states and quantum computers, all that stuff. So like there's something called what is it? It's like a gauge gravity duality. And it's which is like, it's kind of a more general form of holography. But anyway, like it's a really useful idea. So cool things have come out of string theory, like really, really cool and useful things have come out of string theory. Whether it'll give us a theory of everything is a different story.
Right, right. I know Ed Witten. I was reading about Ed Witten a bit. Guy's crazy, genius.
Yep.
Um, but I heard he kind of like melded a bunch of string theories together and made like one M theory.
Yep.
Um, but yeah, that's crazy. Just what would that imply when it comes to strings like that there's like those one-dimensional strings that everything emerges from? Is that generally what it means?
Yeah. So sort of. So if you take string theory as being true, then yeah, it's something like that. But that's not what most people do. And most people who are actually working with string theory are actually working with some form of M theory.
Hmm.
In that you're working, some people say that M stands for membranes or master or whatever.
Hmm.
But the idea is that strings aren't necessarily the only things that exist in some sort of string theory. There's also a string being like a loop of string. You can think of it as like just a loop of string that travels through time. But you could also imagine that you have a sheet of paper, which is two-dimensional, traveling through time,
Hmm.
or a lump of jelly traveling through time. This is a three-dimensional volume. These are called branes. There's P branes, D branes.
P brain.
There are other ones. It's like the letter P. It's unfortunate, but yeah, it's very funny. But I mean, really, like the fundamental things would be strings, and the idea is that they can vibrate in various different ways and represent various different particles. That has some problems, namely, what it doesn't really explain what space-time is,
Hmm.
which is something that we kind of expect to be able to be explained.
Right. That's where quantum gravity comes in, right? Or
Well, string theory is supposed to be a theory of quantum gravity. And
supposed to be one.
yeah. And the reason why you think that, or why you might think that, is because when you're doing this, you write down the formulas for string theory, and there are some consistency conditions. Certain things have to be true in order for the theory to be internally consistent. One of those things that has to be true is that is that the string vibrates in a very particular way, and the way that it vibrates precisely reconstructs or precisely behaves exactly as you might expect a graviton. This is the fundamental particle that would describe gravity. The trouble is it, and I could be wrong here. I'm sure somebody's talked about this, but it's just not something I'm super familiar with. But at least at like the lowest level string theory, the idea is that you get particles that look like gravitons, which is great because now you have a quantum theory of gravity, sort of. But it doesn't explain where space-time itself comes from. It just
Hmm.
explains where propagations, like it just describes where oscillations of space-time come from. Right? Gravitons are like waves traveling on the space-time, not the space-time itself. So you run into a little bit of an issue there,
Hmm.
which, I'm sure people have thought about and people have come up with resolutions for, but I've never seen. I mean, maybe I just need to read more about this. I don't read a whole lot of string theory papers anymore because A, they're very confusing, and B, not relevant to my work. So
Okay. Interesting. Now explain like the holographic principle as well. I mean, what would that entail? And yeah, what would that entail?
yeah, so there's two types of the holographic principle, actually. One is a mathematician's definition, and one is a physicist's definition. So I'll start with the mathematician's definition because it's the most boring, and then I'll get to the interesting one. The mathematician's definition is that you have some sort of system. Maybe it's I don't know. Maybe it's like a pool, right? Like a
Hmm.
pool of water. And then you have some stuff that's happening on the edge of the pool. And to a mathematician, the holographic principle basically just says there's a one-to-one relationship between the stuff that happens on the edge of the pool and what happens in the middle of the pool, which is just saying that basically the boundary conditions determine the interior and vice versa, which is fine if a little boring. It's just a statement about like differential equations. It's really useful, by the way, because it means that you can come up with clever ways to solve hard problems. But it's not like it's not saying anything like profound about the universe. On the other hand, a physicist will say something like, because you can describe the same phenomenon using either the boundary conditions or the interior, they are physically the same thing. They are equally good descriptions of a model, and so we may as well just use one description. And so because physicists think of models, you might say that they are both equally real, and that just as much as we live in a 5 or 4-dimensional universe, if the holographic principle holds, we also live in a 3-dimensional hologram of that universe, and they are the same thing, which is very profound and very philosophical and less really physics, but it's, there's some implications there. How you could tell, I don't even know if you could.
Wow. Yeah. That's crazy. So basically, what it's saying is that part of our existence is also higher dimensional.
It's not part of our existence. It's that our existence is, you can almost think, okay, so I'm going to abuse the notation abuse the language that I said was wrong earlier. You know how you can talk about a quantum thing being a particle and a wave?
Right.
You could talk about you being a 3-dimensional thing in 4-dimensional space and a 2-dimensional thing living in 3-dimensional space simultaneously. They mean the same thing.
Okay.
Which is very confusing.
Yeah. That's crazy. And that's the mathematical perspective of that.
That's
How
the
about
physics perspective. The math perspective is
Okay.
just like, look, the information and what is contained in the other, and so you can learn stuff about one from the other. It's a little bit more boring.
Right. Okay. And then talk about like non-locality.
It's not real.
The universe is not
I
real.
don't buy it. I don't buy it at all. I don't buy that the universe is non-local.
Oh, okay. Gotcha.
I mean,
What would
go ahead.
mean? What would that mean?
Yeah. So yeah, there's an audience here, right? Right. So when we say non-local, there's usually two different notions. One is, well, okay, let me just talk about local. So when we say local, a system is local, there are two different notions. One is that information, matter, waves, energy, whatever, can't propagate from one place to another place faster than the speed of light.
Hmm.
Another perhaps stronger notion of locality is that nothing can transmit faster than the speed of light, even if you can't learn anything about it. So a stronger version of locality would say that entanglement, like the collapse of the wave function under entanglement, it cannot happen instantly, even though you can't recover information from that. Even though that no energy is transferred, even though no signal is sent, a stronger version of locality would say something like, even that's forbidden, because that is some sort of influence propagating faster than the speed of light. So non-locality would just be some form of, well, actually you allow such things. If you allow the stronger, or if you break the stronger form of locality, then you might just have collapse of the wave function propagating faster than the speed of light instantly, perhaps. If you allow violation of the weaker form of non-locality, then you run into some serious problems regarding time travel paradoxes, sleeping with your grandmother, all of these sorts of things. Because now you can talk about anytime something can propagate faster than the speed of light, you can send information backwards, which is
Yeah.
bad.
Or maybe there's some kind of like deeper hidden quantum mechanical understanding that defies our understanding of speed of light,
How
perhaps.
do you follow? Or how do you mean?
I don't know. Maybe there's something that happens on the quantum level that maybe like when it comes to entanglement that we still don't understand that doesn't actually contradict relativity. Maybe there's
Could be.
something. Yeah.
Yeah, I mean, it could be. It's really hard to say. But this is all to say, and the only reason I got up in a tizzy about just saying it's not real. There was this Nobel Prize last year awarded to Zellinger and a few others whose names I can't remember because their names aren't as fun to say. That were there. They were awarded the Nobel Prize for quote proving that the universe is non-locally real. That's only true if you accept the Copenhagen interpretation. If you don't accept the Copenhagen
Mm,
interpretation, that's not the consequent. Like their experiments are still correct. The data is still true. It's just you don't need a universe that's not locally real in order to explain the observed phenomena if you take the many worlds interpretation seriously, for example.
right. Okay. And then when it comes to dark energy, I just had a quick question there. I mean, is there any consensus in science as to what that could be? Is it like a property of space-time itself? Is it
So it's a good question. The There is probably consensus, or rather, no, I shouldn't say consensus. If you ask everybody who's not trying to come up with models of dark energy, they will say that it's a cosmological constant arising from the 0 point energy of quantum fields.
Mhm.
Probably. Some of them may also say it's a cosmological constant that just is what it is because the Einstein field equation just has that built in. Um, those are probably the two most popular answers. I would probably fall into the latter category because I like my fields classical and I like my quantum well behaved. I don't like the idea of 0 point energy ruining things. It just seems messy. Um, but and that is that model, a cosmological constant model, whether it's resulting from quantum fluctuations or if it's just part of built into the universe. That is the model that seemingly is most consistent with the data. That's where the lambda in lambda CDM comes from. The lambda is the cosmological constant. It's the Greek letter that we use to represent that. But there's a huge group of people who are actively working to try to come up with alternative models to explain what dark energy is. Maybe it's some extra field that we haven't detected yet that has some like sort of scalar field or something like that. There are a whole bunch of ideas like phantom energies and quintessence, all of this lovely stuff, which are all great ideas. All you have to do is make sure that whatever model you come up with fits with the data, and then we can't distinguish it from lambda CDM. So there's a whole cottage industry of people trying to understand this. Keep in mind, dark energy, as far as it's like named, I think it's like 25 years old at most. It's younger than me.
Hmm.
So
Wow. Interesting. And that's because, well, Hubble discovered that the acceleration of the universe accelerating in its expansion. So that was discovered, what, 98, 97, 95?
you're I thought you were talking about Edwin Hubble. Edwin Hubble did observe that the universe is expanding, but the Hubble telescope
Telescope, yeah.
observed that, or yeah, well, the astronomers did. I mean, the telescope's just a machine, but the astronomers observed using Hubble that the universe's expansion is accelerating rather than slowing down, which is what was predicted.
Right. But what a coincidence that Hubble
Yeah.
discovered the expansion and the acceleration. Interesting. Okay. Yeah. Now, when it comes to theism, I mean, I just want to talk about more of that, like your philosophical approach to that. Um, like, what are your best like arguments against God? Like, what is your position? Do you have anything to say about that?
Yeah, I mean, so it really depends on the theist that you're talking to, right?
Right.
I mean, the most bare, but like I gave the argument that I give most frequently to very vague theists. So there's, it's funny. They're the I'm going to insult so many people when I say this. They're the smart theists who come on and try to justify a deistic position first. And if they can
Mm,
get you on a deistic position, well, then they'll start introducing something else.
right.
And then there are the not so smart theists who just point to the Bible, or whatever, point to morality, whatever they
Yeah.
want to do. So if I'm talking to a smart theist, I fall back to that argument about what does it mean for something to exist outside of time if it's capable of change, right? And then we can also talk about, and people will bring up questions about like what came before, and is it possible to have an eternal universe? But at the end of the day, like my pushback is, look, it seems like we can explain our universe fairly well with materialistic methods. It seems like actually it's never failed. We've never unsuccessfully made predictions about our universe using, or we've never not been able to come up with a materialistic explanation for for every single phenomenon that we've encountered. There are some recent phenomena that we can't explain yet, but they're quite new. And the theistic position has never made an accurate position or an accurate prediction. So we can intuit that way using induction. But beyond that, I mean, we could talk about the problem of evil. That's a pretty good one. A pretty good, I mean, like, pretty good argument against any sort of theistic position. Personally, I wasn't deconverted by anything more than like a silly question. I was raised Jewish, but like I haven't believed in God since I was like 5, because it seemed
Well,
silly. Like one of my earliest memories is one of my earliest memories of religion anyway, is being taken to temple. Me asking my mother if the two men at the front, there were two rabbis at the front, uh,
mm.
is that God? And then she said, no, God is all around you. And I'm thinking to myself, I didn't say this. I'm thinking to myself, that's dumb. Like, like what a dumb idea. Like, no, there's air around me, but there's no God, right? So yeah, I mean, like, it's always just seemed like maybe, I
kind
don't
of,
know, maybe it just seems silly. Like, it seems like a
yeah.
story.
I can imagine you being the young Sheldon Cooper.
Don't do that to me, man.
Yeah, well, that's funny because I actually just kind of went along with it in my life until I was like 20, and I started asking questions about. Well, somebody asked me a question that I
Sure.
couldn't answer, and I was like, wait, what am I doing? Let me think about this. But it's crazy that you're only 5 years old and you were asking that to yourself. I mean,
Maybe 6, who
since then
knows?
you were pretty much you call it like you're an atheist after that,
Well, I mean, like, I never really thought about it. It was just like
right?
this thing that like my mom took me to temple and we would sing songs, and I went to like a secular school, like a public
Mm.
school, at least until I was like 13 or whatever. Um, and I assumed it was just like Santa. Like people talk about Santa, like people on the news talk about Santa Claus, but like nobody actually believes in it. I just assumed that that's what it was. And so I just didn't really have this idea that people, and then I became a teenager and I realized that people actually took this seriously, and I got into arguments with rabbis at school, and the rest is history, as you say.
Oh, like so you went to like a high school that was religious?
Yeah, so 7th through 12th grade, I went to a religious school, which
Oh,
is fine. I learned quite a lot, and I wouldn't. Well, okay, the school shut down the year after I graduated because I didn't have enough money. So it wasn't
oh.
super well run, but like the teachers were excellent, and it was a good environment to be in, and I learned a lot. I just didn't believe any of it.
Wow, interesting. So, okay. So, I mean, your family were they conservative when it comes to their faith, or like were they pushing on you, or
No, my mom. So I mean, I grew up in a roughly single parent household. My mom was like, there's like three types of. Okay, so white guy, right? Jewish guy too. There's three types of white Jewish people generally. There's Ashkenazi Jews is the ethnic group. There's Orthodox. These are going, and there's a few different types of Orthodox. There's the people with the big hats and the curly things, and they wear suits all the time. And then there's the modern Orthodox, which they just wear the little hats and the white shirts, and sometimes they have the curly cues. Those are like the most religious people. Then you have your conservatives, which are not the most conservative. They're like modern, they're like holding on to some tradition but also like growing with the world. And then there's the Reform Jews, which I guess formed in like the 1800s or something. They're like liberals basically. They're like, we got to adapt at the times, keep everything good. We can interpret the religion how we need it to be to fit the modern world and so on. That's why mom was, and still is, I think. I don't know how her beliefs have changed in the last 20 years, 10 years or whatever. But yeah, so no, I mean, she never had an issue with me questioning things. And
Hmm.
interestingly enough, um, uh, Judaism is famous for questioning. There's an old joke, and by the way, like I don't mean to, like clearly I'm very still very culturally still very Jewish, meaning that I still do like the traditions with my mom and stuff like that. It's just
Hmm.
anyway. But there's this whole there's a joke that you put three rabbis in a room and you'll get like four opinions, right? Um, and because and for those who don't know, and I actually suspect this is quite a lot of people. Many people don't actually know very many Jewish people. There's 14 million of us in the world, right?
Mm.
Um, so there's what Christians call the Old Testament and Jews call the Torah, and then there's a whole bunch of there's some other books attached as well. There's like there's prophets, and there's kings and psalms, all these things that everybody's familiar with. But that's not where Jewish that's not the end of the Jewish lore, if you will. There's something called the Talmud. The Talmud is basically, well, you have the Talmud V1 basically, which was written sometime around the turn of the millennium, so sometime between 100 and 300 CE, which is commentary on the Torah, and you have a whole bunch of rabbis arguing about what it means. And then you have the Talmud V2, which is a whole bunch of rabbis 100 or 200 years later arguing about what the earlier rabbis were arguing about, trying
Mm.
to interpret what they were saying. And then there's even commentary that spans up to the last the 200 300 years ago. So you just have layers upon layers of typically men, sometimes women, arguing with each other about what they meant in the past. So like it's like the whole cultural tradition of just like questioning and arguing and debating. And so it's really not surprising that like my mom didn't have an issue with me just
Yeah.
rejecting these ideas because they seemed wrong. Like it's kind of built into the thing.
Yeah, that's really interesting. I didn't know that in particular. And in contrast with Christianity, which kind of gives you the Bible and says, "This is it, guys. Here you
Yeah.
go." So it's interesting. Um, Now, and clearly today you don't really take those books seriously, but um, the last question was like, well, when it comes to purpose, a lot of people when they leave religion, they feel like there's a void in terms of like their spirituality or their purpose. Um, and I always say, well, my purpose is to to live, to explore, to learn, to do these things, and I can make my own purpose. What would you say your like the thing that makes you just feel great to be alive and be human? Like what's that one thing that makes you, or any multiple things that give you purpose in your life?
So I mean, just got to make sure that my wife can't hear me. No, I'm kidding. No. For the longest time, it was legacy, right? Like I've wanted to be a scientist since I was like 9, and
Hmm.
that meant I wanted, when I was 9 years old, I wanted a Nobel Prize. I'm a little bit more reasonable now. Not everybody can get one, right? But I wanted my name on something. I wanted Blitz equation or whatever my actual name is, right?
Cool, cool.
Something like that. And that's still a major driving factor in the way that I operate, because if this is all there is, there's only one way to live forever, and that's to be remembered by people, right?
Right.
In fact, I was actually at a concert the other day, and there's a quote from someone, I don't remember who, but they said this at the concert, namely that you die twice. The first time is when you draw your last breath, and the second time is the last time somebody says your name.
Hmm.
Which is deep and gives you really an existential sense of dread, right? Because think about how many people whose names haven't been said in 1,000 years. It's
Yeah.
most people, right? Yeah, so legacy, learning something new that nobody's learned before. That's like the first time I published a paper. This was a paper with my PhD supervisor. Kind of like the last few months, we came up with something that nobody had observed before ever about our universe. Or rather, it's a mathematical fact. It's not actually about our universe, but it's close enough. And I'm like, hey, like this is it's that there's a certain high you get just from being like, I'm the only one who knows this. So that's like a driving force, just like seeking that out. You can almost like an adrenaline junkie. But on a more humanistic level, I met my wife when I was 18. We've been together ever since. And when I'm not working, when I'm not thinking about physics or math or whatever, or debating on TikTok, it's just I want to spend time with her and hang out with her because she's a cool person to be around.
Oh, nice. Yeah, that's awesome. Um, yeah, it's. I think Brian Greene said it great. He was like, "Science is like when you're peeling away layers of reality that have never been seen before." That's something that's really you can only really get there from a scientific perspective. because the religious perspective is, well, we know the answer, it's God, and then they work their way down from there.
Yep.
But the scientific perspective is like the opposite. It's like we start from scratch and we work our way up, and that approach allows you to not only see more, right, extract more from the universe, but it also allows you to get that sense of like wonder and all reverence for things, because you're seeing things, you're knowing things how they really are, that nobody's ever seen before. Like, so what you said, that's incredible, and I think you'll get a Nobel Prize, dude, if you keep working for it. You seem
I
very smart. You
yeah,
got it.
like
You got this.
that's what you say. When you're on TikTok and you have like a postgraduate degree, everybody thinks you're the smartest person in the room. But then when you go to a seminar and you're
Yeah.
surrounded by all those people, you realize I don't know anything.
Oh man, yeah. Science is science. The methodology of science is simple, but it's a very difficult thing to actually apply.
And it takes a
Um,
certain kind of person. Like
yeah,
honestly, like most the way I spent my afternoon, I had to run errands this morning, but the way I spent my afternoon was I was just reading a paper. Like that's what I was doing,
mm,
and it is filled with equations and phrases. Like I actually still have it pulled up. Phrases like I don't know. I'm just gonna pull out. Consider an NEH delta and introduce on it an affinely parameterized null normal L naught and denote the compatible. Like it's just stuff like that. Like it's just 37
yeah,
pages of that.
yeah,
And so like, there's a certain level of masochism needed to be
yeah,
able to do that. And it sucks. Like sometimes it really sucks. I've been in a rut for the last 2 weeks or so because I haven't made progress on 2 projects I'm working on. And so like, there's a certain degree of persistence that you need to have. And
yeah,
sometimes I wouldn't wish it on my worst enemy, but when you're an adrenaline junkie, I guess like it's worth it at the end.
yeah. If you look back in history, especially the past few hundred years, there's only been a few dozen people that really propelled society forward technologically. Like if you
Technologically, well, I don't even
think,
know if that's true.
well, scientifically, like, well, maybe not a few dozen, but maybe a few hundred people out of billions.
um, that so I guess it depends on what you mean by propelled us forward, right? So like, yeah, there's names like Einstein and Dirac
Yeah,
and
like
Riemann, all these big names that
the
you
ones who
know.
have really changed
But then you go look at their
society.
papers, their foundational papers, and you go look at their citations. There's names on there that you've never seen before. But if those people
Of
hadn't done their
course.
work, they wouldn't have been able to do their thing.
Of course, of course.
So in some sense, like yeah, like there's a few big names, but like it's I don't know who said it, but there's something about standing on the shoulders of giants, right? Like there are a lot more giants than you
Yeah.
think.
Oh, yeah, of course, of course. Um, my point is that my point was that the vast majority of people are not scientists.
Oh, sure.
Um, that's the
Yeah,
point.
sure.
I know every scientist is important, of course.
Except
But my
Steve.
my my point was my point was the vast majority of people in the world, um, typically are not going to contribute to the progression of technology and science and things like that. It's really
That's probably
people in
true.
science. So that's why I appreciate you being here and all that. Um, this is why I promote STEM. This is why I talk about science, communicate about science, um, on TikTok and things like that. So yeah, any final
Worth it.
questions? Any final words?
Um, I don't think so.
Cool. All right, man. Well, thanks for being here. Appreciate your time. I know it's rough. I know it's tough giving your time out, but thank you.
Of
Appreciate you
course.
being here. Thanks for the talk. And hopefully you do this again some other time.
Of course.
All right, guys. Thanks for watching and see you soon. Bye.